So continuity. Let's have a reader. Thank you so much, Aiden, for volunteering.
A function is continuous if you can draw the function without ever lifting. You could pencil the following. Okay. The two types of discontinuities, removable and non-removable. A hole in the graph is an example of a removable discontinuity. It is considered removable because you can easily make the graph continuous again by filling the hole. Vertical asymptotes and jumps are examples of non-removable discontinuities. They cannot be made continuous without drastically changing the function itself.
All right, so we have different types of discontinuities, but the layman terms, you can draw the function without lifting your pencil. So for instance, if I'm looking at this one, I'm tracing along, and then it's like, oh, we got a hole. So I have to lift it and then keep going. You following me? And so when it just has a hole, it's called a removable discontinuity. The hole can be replaced. Does that make sense? That is still a removable. All right. It's still called a removable discontinuity. You have a hole, but you can put it somewhere in that same x value. All right. So that's still removable. Now, non-removable discontinuities are when you have a vertical asymptote, which means the limit is what? Does not exist because it increases and decreases without bounds, or it's a jump discontinuity. All right. It jumped. It literally went whoop, jumped. All right. All right, so example 1. So find the points at which the interval below is continuous and the points at which it is discontinuous on this interval. I want to do discontinuities first. All right. When is this graph discontinuous? At what? At x equals, before 2, 1. It is discontinuous at 1. I would have to pick up my pencil at 1. Are you following me? When else is it discontinuous? At x equals 2. All right. What's going on at x equals 2? It's a vertical asymptote. So my limit does not exist. It does what? It increases without bounds. All right. When else is it discontinuous? At x equals 4. All right. So that's where it's discontinuous. Now, let's talk about the intervals in which it is continuous. So it is continuous from 0 to 1. And it is continuous from 1 to 2. And it is continuous from 2 to 4. And it is continuous from 4 to 5. All right. All right, so now let's talk about the definition of continuity. So this is the mathematical way that I want you to think about it. All right, so the definition of continuity is the limit as x approaches c of f of x is equal to the value of f of c. So just like Ava said, what is continuous? A limit is equal to the value. So we talked about a limit. What's a limit, guys? When you do what? Approach from both sides and it gets arbitrarily close to a number. And before I said, does the limit have to touch? No. But to be continuous, what does it have to do? Touch. It has to touch. So the limit is still going to the same y value, but it's touching now. That's basically what continuous is. All right, does that make sense? And what we see down here is the limit is actually from the what? Left and the right. It comes from both sides and it's actually equal to that value. Okay, pretty good. All right, so layman's terms, you can do it without lifting your pencil. Mathematically, it's a limit equaling the value. Pretty good? Yeah. All right, cool. My limit equal, here we go. All right, so let's look at this example. All right. So for c equals 1 and 2 and 3, I want to figure out my limit as it approaches from the left and the right, and what would be the limit? Okay, so I just kind of want to do this orally. All right, at c equals 1, what's my limit from the right at 1? It's 1. It goes to 1, right? From the left, it goes to 1. So my limit is equal to 1. However, I do have a limit that exists. True? My limit exists at 1. However, what is my value? 3. So my limit as x approaches 1 was 1. However, my value, f of 1, was actually 3. So does my limit equal my value? No, it doesn't. All right? So that's why it's discontinuous at 1. Does that make sense? All right, so let's keep moving. So I have a discontinuity at 2. That's what we talked about on our previous thing. Well, my limit from the right is what? Increasing without bound. My limit from the left is increasing without bound. So the limit is truly does not exist, or I'd accept infinity. So does my limit actually exist at 2? No. So if my limit doesn't exist at 2, do I actually even care about the value? Not at all. All right, it's already going to be discontinuous because I don't even have a limit that exists. You following me? All right, let's look at 4. Well, what happens at 4? What's my limit as x approaches 4? It doesn't exist because it's a what? A jump. So if my limit doesn't even exist again, can I be continuous? No, even though, what is my value at 4? I actually do want to talk about this one. It's 1. So I do have a value. So I do have f of 4 is equal to 1. However, what's my limit as x approaches 4? It doesn't exist. All right. So do these match up? No. All right. So I don't even have a limit. I do have a value in this case, but it's not continuous. Okay? So we can kind of see it on both ways here. All right, let's look at example 3 here. All right. I need a reader. Thank you so much, Nathan. Go for it.
You don't always get a picture, so you will have to be able to do this algebraically as well. Determine whether each function is continuous or not. If it is not continuous, use the definition of continuity to explain why.
All right, so let's look at A. Let's look at A. Where might this function break? At x equals 1. All right. So at x equals 1, my function might break because what am I going to get? A vertical asymptote. I'm going to get a number over 0. You following me? So what is my limit as x approaches 1 of this function? It doesn't exist. All right? Now I go from a little bit from the left and a little bit from the right, and I'm going to get negative infinity and positive infinity, right? So it doesn't exist. So my limit doesn't exist. So do I even care about my value? Not really. So it's going to be discontinuous at what? At x equals 1. All right. All right, cool. Let's look at part B now. So anytime we see a fraction going on, what should we probably do? We should probably factor it. All right. So let's factor it. What does it factor to? Factor to 2x minus 3x plus 2. Very good, guys. All right, so what happens here? My x plus 2's cancel to make a simpler function, right? So where might my problem area lie here? At x equals negative 2. All right? And so if I take a limit as x approaches negative 2, I do get something. Because I substituted in my simpler function, right? I do get that. So if I substitute in negative 2, what do I get? Negative 7. But what's actually happening at negative 2, negative 7? It's a what? It's a hole. All right? I have a hole going on at negative 2, negative 7. Because do I actually have a value of g of negative 2? No. It's a 0 over 0, right? And so I don't actually get anything here. It doesn't exist. So value. It doesn't equal my value. So let's go over my discontinuities again. What kind of discontinuity is A? Removable or non-removable? It's non-removable. All right? Because it's a what? It's a Vertical asymptote. All right. Is B removable or non-removable? It's removable. It literally was removed. All right. It's a hole. All right. Now let's look at C. All right. So where might my problem area be on C? At x equals 1. That's where I might have my domain issue. That's where x is less than 1 on this guy and x is greater than or equal to 1 on that guy, right? So 1 might be my problem area. That might be my problem area. So we need to see where that is. So what's the definition of continuity? The limit is equal to the value. But what's a limit when you do go from both sides? So let's test it. So let's test the limit as x approaches 1 from the left of h of x. If I go from the left, which one am I using? The top one or the bottom one? The top one, because it's a little bit less than 1, right? So I just substitute in 1 there. And what do I get? 1. I get negative 2 times 1 plus 3, which is 1. Now I'm going to do a limit as x approaches 1 from the right. So which one am I using now? The bottom one. All right. So now I just substitute in 1 right there, and I end up with 1. So what must my limit as x approaches 1 be? It's 1. So does my limit finally exist this time?
Yes.
It does, all right? However, does my value exist? Maybe. We haven't tested it yet. So we need to find h of 1. So I need to find out where 1 is defined. So which one do we substitute in? The bottom one, all right? Because that's where it's equal to. Are you following me? So if I substitute in 1 right there, what do I get? I get 1. So what do we know? Does my limit equal my value? Yes. So what do we know about this function? This is continuous. Because why? It's a what? A limit is equal to the value. All right. All right, so now this is the way that we do it a lot in calculus, is with these kind of piecewise functions. All right, so let's look at example 4. So we're going to use the definition of continuity to find the values of a. Sometimes they use different letters than a, so that g of x will be continuous for all real numbers. So what do we need to do? We need to have a limit equal to the value. Well, where might my problem area be on this first one? 1. All right. So I need to find a limit as x approaches 1 from the left, and I need to find a limit as x approaches 1 from the right. So I just substitute in what? 1. So if it's from the left, which one am I using? The top one or the bottom one? The bottom one. So if I substitute in 1 for x, I end up with what? 1 plus a. All right. And then, if I substitute in from the right, I'm going to substitute it in the top one. So, now I end up with what? 8. Does everybody follow me? All right. Now, to be a limit, what must happen? They go to the same number. So, what do I do with this 1 plus a and 8? I set them equal. So, now I'm just going to set 1 plus a equal to 8. So, a is equal to 7. All right. Now, the only other thing that I need to be aware of on these kind of problems is make sure it's equal to at some point. Are you following me? Because it has to be actually f of, or g of in this case. So what do we want g of 1 to equal? We want g of 1 to equal 8. And so my limit will be 8 if a equals 7, and my g of 1 is going to be equal to 8. All right, and that actually doesn't even have to do with a in this case. All right, so the answer to the question, though, would be a is equal to 7. All right, let's look at part B. Just had a quiz over this kind of problem today. So what do I need? To be a definition continuous, it must be a limit is equal to the value. So if I'm doing a limit, which one am I concerned about? The top or the bottom? The top. So if I do a limit as x approaches 1, I'm concerned about the top. But what should we do to this thing? Factor it. Because right now, if I substitute in 1, what happens? we get 0 over 0, right? So we get a whole. All right, so I need to still figure out where that limit is, though. So let's factor it. So what does it factor to? X squared minus 1 and x squared plus 1 over x minus 1. Oh, snap. What do I need to do again? Factor it again. So now I have a limit as x approaches 1 of x plus 1, x minus 1, x squared plus 1 all over x minus 1. But what happens here? X minus 1's cancel. So now I have what's called a simpler function. So now I substitute in 1. And what do I get?
4.
I get 4. I get 4. However, for definition continuity, I need my limit. My limit should be 4. But right now I have a hole going on at 1 comma 4. Well, what should my value be? What needs to be h of 1? H of 1 right now is a. So what do I do with these two things? I set them equal. So a must equal 4. All right, so the first thing, the properties of continuity, all your math stuff works from all the times before in math. Now we're going to talk about extended functions. And so now, before we had a piecewise and then we were asked to do something with it. On an extended function, it's basically, I'm going to make a piecewise. All right, that's really what's happening. All right, so if we look at a, I look at this function. First of all, what are we going to do with this function? I'm going to factor it. All right, so let's factor it. So when it factors, what does it become? X minus 5, x minus 1. Sounds great. Over x minus 1, right? So what happens? My x minus 1's cancel. What does that create? That creates a hole. All right? So it has a hole going on where? At 1, right? At 1, it creates a hole. So that is where I'm going to have an issue. So I'm going to make an extended function. So I'm going to call it something else. We'll call it g of x here. And it's going to be x minus 5 everywhere except for when?
1.
X cannot equal 1. Why can it not equal 1? Because it's going to be a hole. All right? Well, at x equals 1, where do I want it filled in to make a continuous function? If I substitute in 1, what will I get? I'll get negative 4. So now I want negative 4 when x does equal 1. You follow me?
Yeah.
So that is my extended piecewise function to not make my original function break. Does that make sense? So now I'd have a continuous. All right. All right, let's look at part B now. So the same thing applies here. So again, I have a fraction, I have a quadratic. What am I going to do with it? Let's factor it. So what's it factor to? Well, what happened again? I get a hole. Where does it break? At negative 3. So I want x minus 6 everywhere, but x equals negative 3. All right, I can't use it. And so then, where do I want? Negative 9. So now I'm going to put a negative 9 there when x does equal negative 3. All right, pretty good. So there is my extended function to make that continuous. All right, pretty good. All right, we're going to do IVT the next day. Continuity homework A. All right.